Hey guys, so this is night two of uh, the study guide review, or just an overall review of Introduction to Discrete Structures. Um, like I said last time, this is not really a be all end all. I'm not anywhere near qualified to teach this, but what I can try to do is, at the very least, try to help un unravel some of the mysteries and some of the confusing questions when it comes to introduction to discrete structures. So I'll do my best to help out. So last time on the last video, we kind of left off at this idea of propositions. And so propositions really, just for a quick refresher, um, it's just at its core, it has a declarative statement, and the key part of propositions is that it has a truth value. So you can either answer it with a true or a false value, is what we mean by truth value. So examples of propositions: the sky is blue, big can fly, 1 plus 1 is equal to 2, 0 equals 1. Um, all of these statements are propositions because in every single case that we're looking at, every one of them has either a true or a false value. And we were talking about examples of statements that are not propositions. So questions are the most common examples of statements that are not propositions because they can't be answered with a true or false value. So questions such as, what if I am not a human? Well, that's not true or false. It's that's not answered with a true or false. X equals 1 is not a proposition, though I did say that this is a little bit of a special case. We'll still come back to him in the near future. And then the other the most common one that we kind of joke about is this idea of, will you marry me? Will you marry me is not a proposition because it's not a true or false value. It's a yes or no. Another one that I discovered is like basically like kind of commands when you are ordering people around. So sit down, lift the box up. These are not statements that have true or false values. They're actions and they are commands. So they don't have true values to them. And so we were talking about this idea that these are the simple proposition we came up with were the idea, or this idea that they're simple, they have one idea, but maybe we want to have a proposition that has multiple ideas, kind of like how we say sentences in English. We don't have sentences with just one topic, we have sentences with multiple topics. And so the question is, how do we form more complex propositions? And the way we talked about that is with connectives. And connectives are pretty much symbols that just help join propositions together. If you want to think about it in the English terms, they're just kind of like the bridges, for lack of better terms, that help combine multiple statements. And we talked about the most common ones. Again, there are way more than these. These are just some of the most common ones you'll see, at least in a Introduction to Discrete Structures class. So for starters, we have the wedge symbol, which is the and word in English. We have the V symbol. This is no, this is this little symbol here. This is the or word in English. Also, I should mention these are I'm using when I say wedge symbol and V symbol, these are what we call them in a language called LaTeX. So take that with a grain of salt. I kind of refer to them by the LaTeX command sometimes. We have the negation symbol, which is the not word in English. Implication symbol, this is the phrase if then. If something happens, then something else happens. The by implication, this double arrow, this is the phrase if something happens, if and only if something happens. And then exclusive or, which is the symbol, which is also the word or. This is either one event happens or the other, not both of them has that, but not both of them can happen at the same time. And so, like I said in the last video, most likely if you're watching this video or reading this document that I upload somewhere in the internet, you're not an English major. and we don't like writing big statements and sentences because we would like to keep our hands intact as much as possible because arthritis is a thing and we would like to not avoid that as much as possible. So what I came what I left off last time is kind of an idea of how to write a basic and complex proposition. So I had the sentence, I passed introduction to discrete structures and I am a college student. And we can use the idea that of connectives and propositions to help us out here. And what we said is, let's say that P represents the statement, I passed introduction to discrete structures, and let Q represent the statement, I am a college student. And so now my sentence just becomes P and Q. And then the last thing I did before I left it off was essentially I replaced the word and with the wedge symbol, which is the exponent looking symbol. And now I have a proposition that in the logic world, which is P wedge Q, which is much easier to write. And I kind of left off at the fact that sometimes that it's all fine and dandy to have these symbols, but obviously there's a little bit more that we can do than just replacing English stuff. So what I'm going to show you is what I'm going to start off is actually showing you a couple of a couple of things that I was doing in here that I wasn't really representing. So when I say that P represents the statement, I passed intro to discrete structures. So when I say this event, when I said this, what I meant was that wherever I see a P, it's almost the same thing. Well, not almost. It is exactly representing the sentence, I passed introduction to discrete structures. But the question is, how do we essentially store that value into the variable? And just like and the answer is we can look at this from a regular math perspective. So in math, when we store values into a variable, we use like an equal sign of some sort. So for example, x equals 1, we're storing the value 1 into a variable called x. And now x holds a value. Well, we can do the same thing here when we're in the logic world. In the logic world, we can store statements into letters or really anything, really. We have a special name for them, but for now, what we're going to say is that instead, rather than saying P represent the statement I pass introduction to discrete structures, in the logic world or in the discrete in Boolean algebra, I guess, not Boolean algebra. In in other words, what we can say is that P is equivalent to the statement I passed introduction to discrete structures. So what we're saying is wherever we see a P, it's equivalent to saying the phrase I passed introduction to discrete structures. So quick note, this is saying equivalent, meaning in the left side and the right side hold the same truth value at the same time. So when one side is true, the other has to be true. When one side is false, the other side also must be false. They both must be the same at the same time, or else it's a false statement. And why is that the case? Well, we might show this, and we'll show this when it comes to the idea of truth tables. But but in terms of like what this means, this basically means that it's really easy to store rather than writing big sentences and big like functions and stuff like that. We store them in essentially kind of like variables, just kind of like how we do in regular math. So in other words, we can instead of saying like Q represents the statement I am a college student, now Q is equivalent to saying I am a college student. And so now we know that P is equivalent to I pass introduction to discrete structures. Q is going to be equivalent to I am a college student. And that's really useful. And so the question is, what do we do with this information? So no, in the last time we were kind of like talking, we were talking about this idea that um that intro my mind has just run out all the window. Oops. That but the idea is that we can make more complex statements out of this than just um basic one topic propositions. So one of the examples was P wash Q. We could also have another example of a complex propositions. We could say if the sky is blue, then either um, it is sunny or it is not cold. And this is an idea of a proposition because it has a truth value to it. You can say that this is either a true statement or a false statement, depending on, well, what the weather is. And so we could say let P be equivalent to the fact that the sky is blue. Let Q be equivalent to uh, it is sunny. And then we can say let R be equivalent to the fact that it is not cold. And so now what we have essentially is this, we can say a if P, then either Q or R. And this again, this is a lot better than having to write all of this out, but we want to be even more lazier. We want to make sure we want to write this in as little steps as possible without having to worry about essentially like breaking our hands because, well, we're lazy. Oops. So notice that this time there's this if then statement. Well, that is a sign that we should use the right arrow, which is the implication symbol. So really, what we can say is that we can say that P implies either Q or R, but or is the V symbol. So we could really just say in parentheses Q or R. And this gets the point across just as effectively uh, without any English statements. We can say that P wedge Q V R is the same thing as saying that if the sky is blue, then either it is sunny or it is not cold. And that's really powerful. So now the next thing I want to talk about is this idea of order of precedence. So order of precedence. Um, and what do I mean by that is basically there's this idea that just like in regular math where you guys had to do PEMDAS, or let's call this order of operations. Let's call this order of operations. So remember, we are in essentially, remember, at right now, we're essentially doing in quote unquote basic Boolean algebra. That means all statements evaluate either to true or false. All propositions, I should say, all propositions. All propositions that we create evaluate either to true or false, because those are the two main values. In fact, they're really only the two values of Boolean algebra. And so the question naturally becomes how how do we evaluate Boolean expressions? Which means like how do we evaluate the validity of a statement such as this, like P with implication Q or R, for example. So for example, let me show you guys what we mean by Boolean expressions. For example, a Boolean expression might look like the following. So we could have, and try not at the current point we are, don't worry about evaluating it right now, but just keep this statement in the back of your mind. So we could say the Boolean expression could look like true or false and true. Um, yeah, we'll start with that. Just to keep it nice and easy. So, how do we evaluate this? Well, we look at all the Boolean essentially we look at all the Boolean operation uh are listen, we'll call them all the operations that are happening. So those operations would be like, for example, either some sort of XOR, some sort of by implication, implication, negation, any of those. Um, the order of and we evaluate in the following. We evaluate operations in the following order. Or in following order. Priority. Note that when we that the highest priority is going to be number one, while the lowest priority is going to be the last number. So the order of operations is as follows. We have essentially set at the top, we're going to have the negation. Then we're going to have the conjunction, then the disjunction, then the implication, and then at the bottom, we're going to have the biconditional or the exclusive or, either whichever one we have. This is known as XOR. And the important note is this. The important note is that um, the use of parentheses could and most likely would modify any sort of order of operations. So the reason is simple. Just like how in PEMDAS parentheses comes first, whatever's in the parentheses has to be evaluated first. The same thing here is applied in Boolean algebra. But the connectives in the parentheses have to be evaluated first. So when we look at the statement, when we're looking at this statement right here, true or false and true, note that there is no parentheses. So we would do the conjunction first, as it has the higher priority over the other symbol that's present, which is the disjunction, has the higher precedence over the disjunction symbol. But the question becomes, well, what does it evaluate to? So it's all great and dandy to have these order of operations and knowing when to evaluate them. But then the question just naturally becomes, well, what does it evaluate to? What do the wedge signs evaluate to? And that leads me to essentially the idea of what are called truth tables. Again, truth tables. So now the question becomes, what is true or false? What does true wedge false v false, my goodness, true v false wedge true refer to or evaluate to. And to answer this, we're going to need obviously the truth tables. So to answer, we will need to use truth tables to help out here, help us out a little bit. So truth tables are simple. They truth tables are a brute force method. This is a brute force method that tests every single possible combination of truths and falses, true and false, true and false. And the idea is that they essentially, for lack of a better terms, for lack of a better terms, they ensure to us that uh, basic law reasoning and logic holds. They're essentially the training wheels of introduction to discrete structures. So every single, for lack of a better terms, for lack of better terms, there we go. So for every single symbol, every single connective that we have, every single connective has a truth table associated with it. For example, the wedge symbol has the following truth table. And let's show that with this. So what I'm going to do is I'm going to simply insert a truth table. And what we're going to say is that suppose we have two events P and Q. So what we would have to do is we would have to generate every single possible combinations of truths and falses that we could have. So what I'm going to say is that, and I want to know what P wedge Q evaluates to in every single scenario that happens. So what I'm going to do is I'm going to create a truth table, and essentially we can kind of let's think of this from the logical perspective. So let's say that this is P, this is Q, and I'm going to center this. Boop. And what I'm going to do is, and I'm going to actually create a third column for P wedge Q so we can see this. So, for example, I could say that event P happens, so it's true. I could say that event Q happens, which is also true. So the idea is that if both events have happened, I know that event P and Q has to happen, because if both of them happen individually, then from a logical perspective, the event P and Q also has to happen. So we know that this evaluates to true. But just as, oops, nope, that is not what I wanted to do. There we go. Which is as follows down there. So I'll say that this is true. This is true, and this is true. And so listing all scenarios gives us the following. So we have true. If both event P and Q happen, we know that P wedge Q has to happen. But maybe it's the case that P happens, but Q doesn't happen. Well, if event P happens, but event Q does not happen, we know the event P and Q can't happen, because the key word with "and" is that both of them essentially have to be true in order for the event to hold, for the event P and Q to hold. So since one event doesn't work, since event Q doesn't hold, we know that the event P wedge Q should not hold, meaning that P wedge Q is false. And we kind of just like repeat this um, for all the possible combinations. So we could say that it's P doesn't have to happen. You could say that P is false and Q is true because what if event P doesn't happen, but event Q doesn't happen? Well, since event P doesn't happen, then P and Q shouldn't happen either because one of the events doesn't happen. So this is also false. And then the last one we have to kind of like worry about is what happens if neither of them happens. Well, if neither of them happens, then the event P wedge Q can't happen because well neither of the events happen. So we know that it's a false statement. And so this is our example of generating a truth table for the wedge symbol. Regardless of what events P and Q are. It doesn't matter what events P and Q is, as long as we have two events that is connected by an and symbol, we know that it's going to evaluate to true when both the events happen and false is everywhere else. And everything, and we can repeat this essentially. We can repeat this for all the connective symbols. It's not just like how it's not just the case that what the and symbols the special one. Every one of these guys has to have them. So kind of we can repeat them. So we'll do the V symbol, which is the V symbol, which is the wedge. So again, suppose I have two events again, called P and Q. I want to find the truth value, the truth value of P wedge Q, no matter the situation. So the truth table below lists the following. I can't spell. So list the following. So again, we're gonna kind of like take this essentially because it'll follow a similar pattern because P you could have it where both P and Q are true, where P happens and Q does not happen, where P does not happen and Q happens, and then when P and Q don't happen. The only thing I'm going to change is the final column. So when we're doing P wedge Q, now when for a wedge or for V to evaluate to true, only one of them needs to be true. So since both events happen, we know it's true. That doesn't change. But now this guy here, PVQ, since event P happens, we know that either P or Q happening is true because we know one of the two events is guaranteed to happen, that being event P. So now this changed to true. And in a similar way, when we look at this guy here, we know that PVQ is still going to be a true statement because we know one of the two events happened. In this row, that's event Q. However, when we look at the final row, when both of them are false, we know that neither event happened. So we know that the event PVQ cannot have happened because PVQ requires at least one of the events to be true. But since neither event happened, we know that PVQ cannot happen as well. And so now we have enough information to kind of answer this question here of what does this evaluate to? So using those truth tables to evaluate them. So now we can evaluate this. So keeping in mind that we need to have the conjunction happen first because conjunction has a higher precedence of order than the disjunction, we can say that evaluating the statement below, we can say that this is really well, I know I need to evaluate false and true first. And according to my truth table, false and true gives us false. So we know that this is true or false. And now I need to evaluate what true or false is. Well, true or false gives me true. So according to the truth table for the V symbol or disjunction, so we know that the ultimate state validity of this Boolean expression evaluates to true. And so that's a basic example of Boolean algebra along with some of the truth tables. And now, obviously, there is a lot more when it comes to evaluating truth tables. So we, for starters, there's four more symbols that we need to list out. So let's show in the other four truth tables. Or truth tables for the other four symbols. What we have is the first one I'm going to talk about is for let's show the implication symbol. Let's show the implication symbol. And this one's actually going to be a little bit weird. So what I'm going to say for this one is, and this is the one that students, and I will admit myself, gets confused from time to time. So if you get confused about this, don't worry. Um, think of the implication symbol as a contract. Contract. The contract says that if P happens, then Q has to happen. So this is the contract that we're working with. And we'll still have the same truth values, P being true, true, false, false, and then Q being true, false, true, false. But now we need to see the idea with P implies Q is that we're evaluating whether or not the contract holds. In other words, is the contract valid? So let's take a look at this. When if P and Q are true, then the implication statement P implies Q. Well, let's think of it kind of from this example. Suppose, for the sake of argument, that P is the statement, I did my homework, and then uh, and Q is going to be equivalent to the statement I went to, and for the sake of copyright, I'm going to change the name. I'm going to say that we went to NISD. Don't want to get copyrighted. This is not my original word. This is the professor. This is my former professor who I currently TA for. This was the word that he came up with. So all credits to him, none to me. I just kind of took this. But the idea is this. If we plug in what we know, what the statements that we have, essentially what we have is that if I did my homework, then I had to have went to NISD. So I did my homework. It says that I did my homework in this scenario, and I got to go to NISD. So does the contract hold up? And the answer is yes, because the contract says that if I did my homework, then I should have went to NISD, and it turns out that's the case. So we know that in this row right here, P implies Q is true. Now let's talk about this guy. This guy says that if I did my homework, however, I did not get to go to NISD. And the question is, does that violate the contract? The answer is yes, it does violate the contract because the idea is that, remember, the contract says that if I did my homework, if P happens, then I should have went to NISD. Q has to have happened. Well, I didn't get to go to NISD even though I did my homework. So I know that the contract is a lie. It didn't work. It's the idea of my parents lying to me. They just got me to do homework for free. Sad face. Um, but that's the idea with that vote. So now we move on to the the next one. What happens if I didn't go? If I didn't do my homework, but I got to go to NISD. This one's a little bit um complicated. So this one's a little bit tricky actually. So remember, the contract says that if P happens, then Q has to have happened, but it doesn't say what happens if I don't get to what happens if I don't do P. Nowhere in this contract says, oh, also, if you don't do your homework, then something bad or something good happens. So, kind of like by nature, technically the contract holds because the contract never stated what happens if I don't do my homework. So it actually turns out that when you have false implies true, it's actually a true statement. And the idea is because there's nothing in the contract that says what happens if the first event does not happen. In the discrete world or in the logic world, we call this vacuously true. So the idea, and I'll write this down, um, the idea of vacuously true, that is the idea that essentially, no matter as long as the precondition never occurs, meaning P is false, then the whole statement meant P implies Q always evaluates to true. Because the idea is that, well, they just, nothing happens. And then the final one is really what happens if P and Q are both false. Well, if P and Q are false, because of by nature of vacuously true, we know that actually the contract still holds because, well, there's nothing in the contract that says that there's nothing in the contract that says what happens if P fails to have happened, which is the precondition. So since there's nothing in the precondition that has happened, well, it's a true statement. And so this is our truth table for the implication, which is really weird. And yeah, it's a little bit confusing. And trust me, it sort of becomes a little bit uh, more complex, I guess you can say. We'll kind of have it. Um, we kind of try not to think about it too hard. Um, but I think I will kind of leave it at that part for now. And for the next video, what I'll do is I will show the other truth tables. Again, I apologize for keeping these videos short, but I want them to kind of be like small little tidbits. That way it's a little bit more digestible. Plus, I feel the exhaustion already kicking in after a little bit of a long day. So what I want to do is just kind of have this out there. And next time, I promise next time we'll talk more about truth tables and how and what they contain. And then we're going to start talking about what are called laws of logic, rules of inference, and we're also going to take a deeper dive into um, Boolean uh, Boolean algebra evaluation, and yeah, that's pretty much what I have in store. But I do apologize if this video was a little bit disorienting. I guess that's what happens when I went on 3 hours of sleep, but I hope this video helps a little bit more explaining the basics of Boolean algebra. And until next time, I'll see you guys on the next video. Take care, guys.